Alright, hello everybody, welcome back to another video of Tutor Bros. So, this episode is going to be on circuitry. So, I guess we'll start off with a brief introduction to circuits. So, the classic circuit is technically drawn like this. So, this is what we call a battery. And how you could take how you can take some notes about this is that that's the positive and that's the negative terminal right here. And how can you tell the difference, you might ask? Well, if you take a look at this, these are long, and if you look at the other side, these are short. And the shorter ones are the negatives, and the longer ones are the positive. And the thing is, if you have like a circuit that goes around, and I don't know, maybe we'll have like a resistor in there, the funny thing is, current flows like this. Current will flow from the positive to the negative like that. What's interesting is that in reality, it's not the positive charges that are moving, it's actually electrons. As we know, negative charges are actually flowing the opposite way, where the negative charges are actually flowing from the negative to the positive. The reason why we always solve circuit problems as if it's from positive to negative is because of the fact that for thousands of years, people have thought that positive charges actually are the things that move, not electrons. In fact, it was discovered that electrons are the things that move like 50 or something years ago, in like 1940 or 1950. But the thing is, because of the fact that we've been thinking about positive charges moving for like 50, actually no, not 50, like 500 or even 3,000 years, definitely a lot more time than like 50 years ago. So because of that, we've always thought that positive flows to negative, we solve circuit problems like that. Because all the proofs involve this charge moving from positive to negative. But just something to note, because in real life, of course, we know that the electrons are the things that move, not, so that's correct, and the things that positive flow that way, this is technically incorrect. So although this is incorrect, that's what we have to deal with because of the fact that scientists use this because we've been doing it for so long. So with that aside, let's just start jumping right into a circuit. So of course, drawing a battery, positive, negative, positive, negative. Let's draw that same circuit again, this time with the values. So that's a resistor right there. Let's call this battery a 5-volt battery, and let's call this a 10 ohm resistor. Now, one of the main formulas that you're going to learn with circuitry is V equals IR, or voltage is equal to the current times the resistance of the circuit. Now, this is what most people write it as, but it's actually net voltage is equal to the current times the net resistance, because you might have multiple batteries and you might have multiple resistors in a circuit, because then in that case it would be net R and net V. But to simplify, we always just write it as that. But to jump right in, we'll just plug in some things. So we have the 5 volt right there. So 5 is equal to, we don't know what the current is, but we know that R right there is 10. So we plug that in, and we get that the current is 0.5 amperes, or amps. And that's just the unit of current. Of course, the unit of resistance is just ohm, and the unit of voltage is just volts. When solving circuit problems, you're going to have two really big cases. And those cases are either when the resistors are in series, so like for instance something like this, I guess, when they are together, and this is called a in series, so series, well, in series. And then the other case is when you have a circuit that looks like this. Resistors split off into a branch. So they do something like this, I guess. And this is called a in parallel kind of circuit. And there's two different ways you solve this, and I will show you both of them right here. And what's interesting about this is that there's two different formulas that are used to solve these kind of problems, and I guess we'll start with the in series real quick. If you look at it, let's see, nope, that's not right. How do you add a new page? Alright, So if you take a look at this, you have a circuit that, I don't know, maybe has, again, a 5-volt battery. But let's say that this resistor right here has a 10 ohm, like our first example. But let's say that over here we have another 10 ohm resistor. In that case, we'll have to use the net resistance is equal to the sum of the total resistances. So whenever you have resistors in series kind of problem, you just add them up basically. It's not that hard to do. Just never forget that. And then after that, it's pretty straightforward. We have 10 plus 10 is 20, so that's just 20 ohms right there. And then we just do V equals IR again. We have our voltage is 5 volts. Well, 5 volts is equal to our whatever our current is times our total resistance, which is 20. So for this circuit, our current is 0.4 amps. So yeah, that was fairly straightforward. Let's do another problem right here. So let's see. I literally forgot how to add another page. Bear with me here. Alright, so when solving this next circuit, let's call them in parallel, right? When you have resistors that branch off like this, you have to use a, I guess, reciprocated reciprocal formula, and I'll just show you what that is. So let's say that these are still 10 ohms, right? When solving a circuit like this, you have to say that the net resistance is equal to 1 all over the individual reciprocals. So what this basically just means is that you would add these two up, but flip them first. So if you were to flip this, that's just 1/10, right? If you were to flip that, you would get 1/10 as well. So if you were to add those two, 1/10 plus 1/10 is equal to 2/10, which is equal to 1/5. And we have to do the inverse of that, or the reciprocal, and that's just equal to 5. So our net resistance would just be equal to 5 here. Now, if you have that your total resistance is 5, we just plug it into V equals IR one more time. Of course, we had a 5-volt battery. We still don't know, but our resistance was 5. So you plug in 5 this time so that you get your current is equal to 1 amp. So this looks fairly straightforward. We already basically know how to do the beginning parts. And these are the two main forms of circuits you'll see, and most of the time they'll just combine both of them together, which I'll show you right now. So if you have like a circuit, which I don't know, like, I suppose it'll look like this, I guess. Let's see. A battery, a resistor, and then it splits off into 2 branches, like this. And what you'll do here is, let's call this 5 ohms. Let's call this, I don't know, 10 ohms and 10 ohms once again. And let's call this still a 5-volt battery. Now, in this scenario, you would basically just do series and resistors in parallel at the same time. So what I tend to do is just split it up into like separate things. Take a look at this and consider it as one resistor. How do you calculate the resistance of that? It's just 1 over 1/10 plus 1/10. We already know that this is just 1 over 1/5, so that is just 5. Oh wow, that's a really bad 5. 5, right? So you have that value is equal to 5. This value is also equal to 5. So what we would do here is we treated these as in parallel, but when you look at the total circuit overall, you would have to treat this as one resistor, and you'd have to treat this as basically one giant resistor, ignoring that they're in parallel. And we know that this has a value of 5, right? Because 5 was right there. So what you do next is, of course, just 5 plus 5 is equal to 10. And if you didn't follow me there, it's actually pretty simple. Just make sure you calculate this value first, and then you just add it to that. And the reason why is because this parallel thing right here is in series with this giant circuit over there. I know it's a little messy, but hopefully you'll understand it. If not, I'll just go over it one more time, I guess. So let's just say you have like a circuit here. So that's your battery. I'm going to do the resistors in a different color real quick. So let's call that one black. It's not right. Let's call that one that. And let's make sure that this next one is a different color. So I guess dark blue. And actually, wait. Okay, let's see. Let's re-branch that out. So this should look like this, right? Bear with me for just a sec. Now, when you look at this circuit, we treat this as one resistor. One resistor. And then we treat this next one as one resistor as well. So this could technically be simplified into just one circuit that looks like this, basically. It can be simplified to something that looks like this. And we already know how to solve this. This is just resistors in series. But this right here is just that blue thing right there. So we just changed that blue resistor into this simple resistor right there. And that's how you would simplify circuits like that. Now, the more commonly confused thing is how current splits. Whenever you have a circuit that has resistors in series, so for instance, something that looks like this, the current throughout the circuit stays the same. So remember how in our worked example we found that if that was 5 volts, that was 5 volts, well actually no, that was 10. So if that was 10 volts, 10 ohms, and that was 10 ohms, we said that the total current would just be 5 divided by 20, so 0.4, remember? So if your total current is 0.4, you would basically use V equals IR for each individual one to solve it, right? So whenever you have resistors in series, your I is always going to stay the same. And that's just something that's been proven through experiments, and you can find this yourself. You could actually use like a PhET lab, I guess, a PHET lab, and then prove it. But if not, you could just take my word here. Whenever they're in series, just make sure that the current stays the same. That way you can do something like this. Notice how this is 5 volts, alright? If we have that our current is 0.4, and the resistor of this is a value of 10 ohms, right? Well, 0.4 times 10, right? That's just 4 volts. And if you look over here, 0.4 times 10 is also 4 volts. So let's see. Wait, did I do that right? Wait, let's see. 5 over 20, 1, 4. Oh, whoa, I did not do that right. Never mind, I apologize. That's not a current of 0.4. Because if you take a look, 5 over 20 is just 1/4, and that's 0.25. Oh my god, I'm so sorry about that. So if you have a current of 0.25, right? You would change, well actually no, that's still 10 ohms, right? So this value right here, V equals IR, if you have that your I is 0.25 and your R is 10, right? If you multiply those together, what do you get? You get 2.5. What about this? Over here, it's also 2.5, right? Volts, because you just use V equals IR right there. And once you plug that in, you will get that 2.5 plus 2.5 is equal to 5. So that's one funny thing about circuitry, is that your potential difference throughout the entire circuit must equal 0. So basically, the current will flow like this, basically. It flows through here. The moment it reaches that resistor right here, it will have a minus 2.5. So as it flew through that, you have 2.5 remaining. And then it keeps flowing. Then it keeps flowing. And the moment it flows through this, you have another minus 2.5. And then you get left with 0. And then it goes back, it touches the battery, and it just restarts all over again. And it keeps going on and on and on. And that is how circuitry works. So I guess you could think of it as a conservation of charge, which is also a conservation of energy in a way. And that's how you would solve all circuit problems. So if you have like a parallel thing, a parallel circuit, going like this. Let's say that, I don't know, you have a 5 ohm resistor and a 10 ohm resistor. Let's say that the battery has, I don't know, like a 6-volt battery, just for numbers' sake. I'm going to add another page here. Let's first calculate the total resistance of the circuit. 1/10 plus 1/5, that's just equal to 3/10, right? And we have to put that to the negative first power, so that's just equal to 10/3. So your total resistance is equal to 10/3, right? Our total voltage is 6, so we have V equals IR. So we have 6 is equal to I times 10/3. We multiply that over. I is equal to 18/10, or 1.8. So we have 1.8 as our current for this circuit. Notice how our ratios for this work. You have a 5 ohm resistor and a 10 ohm resistor. What my strategy for solving current problems is this. You always have that whenever you're going through here, if you take a look at Kirchoff's second rule, it says that whenever you have a circuit that splits, your potential difference must equal the same. So this must equal 6, and that must equal 6. And where did I get the 6 from? Well, since we treat this as one resistor, right, the same concept that we used in the last problem, we have to make sure that that subtracts to 0. Because remember, our current flows like this. It flows through, hits a resistor, loses some voltage, and then it flows out, and then it must reach that with 0, right? There's only one resistor here, this giant thing. So this giant resistor must use up all 6 volts, basically. So that's why I say it's 6 and 6. Now, if you take a look at this, if we have V equals IR, right? If we have V equals IR, yeah, that's way too thin. V equals IR. We have our V is 6. We don't have technically an I, but let's just call this I times 5, right? Notice how this current would then be equal to 1.2. Do the same thing here, V equals IR. Plug in 6 is equal to I times 10. Notice how I is equal to 0.6. Here's a little cool thing for you. What is 0.6 plus 1.2? Well, it's 1.8. And notice that right here, we got our current is equal to 1.8. So that's cool. Funny thing about circuitry is that whenever you have, oh god, that's hard to see, but you know how we have 0.6 here, and we have 1.2 there? When you have a circuit, it always splits in ratio. So if you have, well, this was 10, right? And this was 5. What is the ratio of that? 10 to 5. 10 to 5 is just equal to 2 to 1, right? Add these two numbers up after simplifying. It's 3, right? Divide your total current by that number. 1.8 over 3 is equal to 0.6. Now, our circuit was originally a ratio of 10 to 5, or 2 to 1, right? When you're splitting the current up, flip that ratio around, so it's 1 to 2. If you multiply that out, that's 1.2 to 0.6, right? Because we have to have that the current value is 1.8. So if it splits 1.2 to 0.6, you're going to have that the 1.2 flows through this 5 right there, and the 0.6 flows through the 10. The reason being, we have to have V equals IR, right? But we know that V stays the same, 6 and 6. So if you have a greater resistance, you're going to have less current flowing through it. So for instance, the 10 is greater here, so you're only going to have 0.6 flowing through. Why? Because 10 times 0.6 is equal to 6. Versus here, you need 1.2, because if you had 5 times 0.6, that would be 3, not 6. Therefore, you would have 5 times 1.2 is 6, and that's how you solve that. So how I visualize it is just 10 to 5, that's just 2 to 1, and then you flip that around later, 1 to 2, and then the current splits in that same ratio, 0.6 to 1.2. And if you notice, I'll just quickly show you, this is 10, that is 5, that is 2 to 1. But if you look at the current is 0.6 to 1.2. If you were to ratio that out, that's 1 to 2. So the ratio switches places. The 2 goes there, and the 1 goes there. So that's how I visualize my circuitry problems. And I'm sorry for the very messy image here, but, oh yeah, I don't know what's happening there. But notice how the ratios flip. So that's basically how you would solve every circuit problem. Make sure that whenever you're going through a resistors in parallel, they will have values that are equal. So V must equal IR, but V stays the same when you're going through that. Whenever you're going through a resistor in series, so for instance, resistor in series here, I guess. No, where is it? So resistors in series, as in this scenario, your current stays the same throughout the entire thing. So the current throughout this entire thing would stay the same throughout the entire circuit. Whenever you split up, like I saw in the previous example, whenever you split up into parallel, you're going to have the voltages the same, versus whenever they split up in series, you're going to have the current is the same. So that's just something to memorize. And that's basically all there is to circuitry. It's a really easy topic once you understand it. Hopefully this wasn't too confusing. I'm sorry for the really messy work here. But that's really all there is to circuitry. Hopefully you guys enjoyed that. Yeah. And make sure you prepare, because if you have a test, well, good luck with that. Circuits isn't too hard, so hopefully this made sense.